All right, continuing on in our discussion of chemical reactions, so far we've discussed synthesis, we've discussed decomposition, and single displacement reactions. We're on to double displacement reactions, and of course we'll cover combustion in another video. So the idea of double displacement is we have two compounds that are made of two parts. They're usually ionic compounds, and they're going to switch. They're going to switch their cations. Okay, so our reactants here then are two aqueous ionic compounds, solutions. Okay, and our products are two new ionic compounds. We're going to switch in our reactants. We're going to switch the positive ions from both compounds, switch them with each other to make two new compounds. Now, there's an important qualification of our reaction products that we have to keep in mind, and that is in this sentence here. At least one of my products has to be an insoluble precipitate, meaning a solid that doesn't dissolve, or a molecular compound like water or some molecular gas. Okay? One of my products has to meet those conditions in order for this to be considered a double displacement reaction. Okay? And that means you're going to need to know something called the solubility rules. Now, there are not very many solubility rules. They're fairly simple, and we'll talk about them in just a little bit. But that's going to help you figure out which of your products is the precipitate. Hopefully you'll recognize molecular compounds when they come in. Okay? Now, this is just sort of like a little bonus additional piece, but double displacement reactions, sometimes you'll see them referred to as metathesis, which is like an old name for double displacement. But if you ever see that in a book, that's what they're talking about. Okay? So here are some examples. I want you to stop the video and I want you to jot these down as usual, as before, and leave some space underneath so that we can write the equations. Okay? We have solutions of lead 2 nitrate and potassium iodide mixed together. We have a solution of sodium sulfate added dropwise to a solution of barium chloride. And we have a carbonic acid solution that we're neutralizing, if you remember what neutralization means, by adding some lithium hydroxide solution, which is a base. So go ahead and stop the video, write these down, and leave some space and we'll write some equations. Okay? Are you ready? Okay, so our first one says that we have a solution of lead 2 nitrate. Again, I'm going to write my formulas fairly quickly because by now you should know how to do that. And if you don't, go back and watch the formulas videos. They're on my YouTube channel. So, lead 2 nitrate, Pb, NO3, 2, aqueous. Potassium iodide, Ki, aqueous. So what's going to happen here is the lead ion is going to switch places with the potassium ion. Now this is +2 and potassium is only +1. So when I write my products, I have to keep that in mind. Lead and potassium have different charges, which means that the products are going to be different. Lead +2 goes with iodine to form PbI2. Now I know there's no 2 here, but that's okay because when I write lead 2 iodide, it has to be PbI2. And potassium with a +1 goes over here to form KNO3, potassium nitrate, +1 and -1. And I know there's a 2 there, but I can't write KNO3 2 because it doesn't exist. I'm going to take care of those weird numbers by balancing the equation. Okay, so I'm going to put a 2 in front of the KNO3 because I need 2 potassiums. I need 2 nitrates over here. That gives me 2 potassiums, so I'll put a 2 there. That gives me my 2 potassiums. It also gives me 2 iodides, which I have right here. Okay, that's the balanced chemical equation. Now you'll notice I didn't put any state symbols in my products because I don't really know yet which one of these, if any, are precipitate. We will come back to those in a minute, and we'll put them in. Okay? All right, let's do the next one. So the next one we have a solution of sodium sulfate. Sodium is +1, sulfate is -2, so Na2SO4. That's a solution. And we're adding that dropwise to barium chloride. Ba is +2, Cl is -1, so it has to be BaCl2. All right. Again, we are going to, the sodium is going to switch places with the barium. Sodium is +1, barium is +2, so we kind of have the same situation we did in the last example. Sodium will go with chloride, well that's just NaCl. Barium will go with sulfate, +2 and -2, so that's just Ba SO4. When you write your formulas, write them the way you know how to write your formulas. Don't worry about what's written here. I know there's a 2 there, but I don't put a 2 here because when sodium and chlorine get together, there is no 2. It's just NaCl. I'll take care of it when I balance right now. I'm going to put a 2 in front of my NaCl to get 2 chlorines. There they are. And I've got 2 sodiums on this side already, so I'm good. I've got a whole sulfate there and 1 sulfate there, 1 barium and 1 barium. So there I go. All I need is a 2 in front of the sodium chloride and I'm done. Again, I'm not putting in state symbols until I know my solubility rules because I don't know if any of these are soluble. All right, let's do the last example now. So the last one is carbonic acid. Okay. Watch the video on how to write formulas for common acids if you don't remember how to write carbonic acid. Carbonic ends in ic, which means it came from carbonate, which is CO3 minus 2. With H pluses, 2 H pluses needed, H2CO3. That is aqueous. All acids are aqueous. Okay? And to this we're adding lithium hydroxide, Li plus 1. Hydroxide is OH minus 1. That is also a solution. It tells me that in the problem. All right, now, what are we switching places? Well, the positive ion in H2CO3 is H+, and the positive ion in lithium hydroxide is Li+. So I'm going to switch an H+ with the Li+. All right, the H+ is going to come over here with OH minus. Well, H+ and OH minus get together to form HOH, which is the same as H2O. But you can leave it as HOH if you prefer. Okay? Lithium is +1. Carbonate is minus 2. So I have to have 2 lithiums to balance the minus 2 charge in lithium carbonate. Okay? I know there's a 2 there and there isn't 1 there. That's okay. I can balance this. I can put a 2 there. There's my 2 lithiums. There's my 2 lithiums. I have 1 carbonate, I have 1 carbonate. I have 2 hydrogens here and I only have 1 there. So I'm going to have to do that. That gives me my 2 H's from here. That also gives me 2 hydroxides, which I have over here. 2 hydroxides. So I'm balanced. Now for this one, I don't have to worry about soluble precipitates, but I'll come back and put in the state symbols once I know for sure what's going on. All right, so let's go back and let's figure out how do I figure out what's solid, what's insoluble, what's soluble? How do I get through all of that, okay? Let's go figure that out now. So we have to talk about something called the solubility rules. And there aren't many that you need to worry about, but there are a few that are going to be very helpful here, okay? Some things to understand about the solubility rules. First of all, if a compound is soluble, it means it dissolves in water, it will exist as an aqueous solution, and so you'll put AQ. If it is soluble, you'll put AQ. If it's insoluble, it'll be a solid precipitate, and so you'll use the little s for solid. Now this gets a little confusing if you're not careful, because the words soluble and solid both begin with the letter s, but they mean opposite things. Okay? So if it's soluble, if it dissolves, you put AQ. If it's insoluble, you put an s. All right? Remember, at least one of your products has to be an insoluble precipitate. Okay? Or a molecular compound that doesn't break up into ions. All right? Water is a molecular compound. Molecular gases like hydrogen gas, fluorine gas, chlorine gas, oxygen, nitrogen, all of those are examples of molecular compounds that are not going to be solids necessarily. They'll be gases or liquid. Okay? So the solubility rules that you need to know are these. Anything that contains an alkali metal, and we've said this before, okay? So lithium, sodium, potassium, rubidium, or the ammonium ion will always be soluble. Okay? Anything, and if you have a compound that's formed that contains an alkali metal or ammonium, it will always dissolve in water. It'll always be aqueous. Okay? If it contains the nitrate ion, it will always be soluble. Pretty cool, right? Those two right there will get you through about 90% of your examples. The other one that you're going to come up with occasionally is halides. So anything that contains chloride, bromide, or iodide. If it contains one of those three, it's generally going to dissolve, unless it's with one of these 3 ions: silver ion, lead 2, or mercury 1. If it's with any of those, then it's not soluble. It'll precipitate. So chloride with silver, silver chloride, precipitates. Okay, it doesn't dissolve, it's solid. Anything else you can assume is going to not be soluble. It's going to be insoluble. It's going to be a solid, unless I tell you otherwise. Okay? All right, so we need to go back now and see if we can figure out, using our solubility rules, which of our products will be the solid and which one will be aqueous. All right, so here we are with our first example. We had lead nitrate and potassium iodide interacting, forming lead 2 iodide and potassium nitrate. Okay, using our solubility rules, potassium nitrate, not only does it contain an alkali metal ion, but it contains nitrate. Both of those means this is definitely going to be soluble, aqueous. What about lead 2 iodide? Well, it contains iodide, which is one of the halide ions. Iodide is usually soluble. The halides are soluble unless they are with silver, lead 2, or mercury 1. Well, this iodide is with lead 2. That's one of the exceptions in which it's not soluble. It's actually a precipitate. So this is my precipitate in this reaction. Okay? Precipitate. Sometimes precipitate is abbreviated PPTE, just so you know. Okay? That means if I take this is a colorless solution, and Ki is a colorless solution, and I mix them together, I get a bright yellow solid forming, and then in a colorless solution. It's a kind of cool thing, and we'll take a look at that reaction later on. Okay? Well, what about the next one? So we had sodium sulfate and barium chloride. We formed sodium chloride and barium sulfate. Okay? Sodium chloride contains an alkali metal. That means it is aqueous. Barium sulfate, we didn't know anything about sulfates, but I said basically, unless I tell you otherwise, you can assume that if it's not one of the cases we talked about, if it doesn't contain alkali metal, it doesn't contain nitrate, and it doesn't contain a halide, it's going to not be soluble. It's going to be a precipitate. So this is my solid precipitate, that one right there. PPTE, precipitate. Okay? Last one. We have our carbonic acid and lithium hydroxides. We mix them together. We switch the H plus and the Li. HOH, well, that's just water. And water, we know, is not made of ions, even though we pretend it is to make things easy. It's really not. It's a molecular compound. It's a liquid. What about lithium carbonate? Is that soluble or insoluble? What do you think? It contains lithium, which is an alkali metal. Alkali metals are always soluble. They're always aqueous. So there's our state symbols for our products. So using the solubility rules now, we can predict what our products are going to look like. And as long as one of them is not aqueous, okay, one can be aqueous, but the other one has to be solid or liquid or gas. It can't be aqueous in order for this to be considered. Well, what happens if you come out with 2 aqueous on the side? Then nothing has happened. It's not a reaction. Even though you can write it as a reaction, it isn't one. All right? You'll have to practice a little bit to get the hang of this, but once you do, it's pretty easy.